Hey everybody, we're going to be going over example 4.3 from the notes, and here we go. First of all, one thing that we just need to remember at the start of this, because it starts asking us about centripetal forces, we need to remember that the equation for centripetal acceleration is speed squared over the radius. So that v right there, that is the linear speed of your object, and this r is the radius of your circular motion. Remember, this equation is only applicable when you have something traveling in a circular motion at a constant speed. Okay, so centripetal motion. All right, so part A asks us calculate the centripetal force exerted on a 900 kilogram car that negotiates a 500 meter radius turn while it's going 25 meters per second. So we know through Newton's second law that the net centripetal forces acting on an object are going to be equal to their mass times the centripetal acceleration. So we know the mass already, and it's just asking us to solve for this whole term over here. What is the net centripetal force? So we know the mass, but we need to figure out what the centripetal acceleration is. So we can substitute that expression in there. Right? We can take this v squared over r and substitute it in there. The reason why we know to do that is we have a speed and we have a radius. So, we want to use the quantities that we're given. And now it becomes just plugging in our values and chugging away. So the mass is 900 kilograms. The speed is 25 meters per second squared, and the radius is 500 meters. And when you multiply all that out, we end up with a net centripetal force of 1,125 newtons, which is exactly what it was asking us to solve for. All right. Now the second one, it gets a little more intricate in that it says, assuming the road's flat, so there's no angles or anything, find the minimum static coefficient of friction between the tires and the road that keeps the car from sliding. So it's asking us about friction and forces, so we want to draw a force diagram. Okay, now drawing a curved car head-on and all I'm terrible at that. So we got this picture. We're just going to use the car in the middle. So if we draw a force diagram for that car right there, we have its weight going straight down. We'll call that mg. We have its normal force for the ground acting on the car. And then the force of friction acting on the car, or the friction is going to make sure this thing doesn't slide off and crash. So the friction is a centripetal force. It is pointing towards the center of that circular motion. And if these are the only forces acting on the car, obviously we neglect air resistance and stuff like that. The car is not accelerating up or down, so these two vertical forces must be equal in magnitude. Okay? And so the question says to find what is the coefficient of friction. So right away I know, okay, it's asking me coefficient of friction. Well, the one equation I know that talks about coefficients of friction is the fun equation. So the force of friction is equal to the static coefficient of friction times the normal force. So if I'm being asked to solve for the coefficient, we can do that right now. And that's equal to the friction force divided by the normal force. So we don't really know any of these yet, but we can figure them out. The normal force, if you look at our force diagram, the normal force is equal to the force of gravity. Right? So if it's a 900 kilogram car, then the force of gravity is 9,000 newtons, which means the normal force is also 9,000 newtons. So we can plug that in for the normal force, 9,000 newtons. We got to figure out what the friction force is now. Well, the net force in the centripetal direction, right, if we go with Newton's second law, let's do it in a different color. Net force, right, is equal to 1,125 newtons. That's from part A. Well, the only force pointing in the, like, towards the center of the circle in the centripetal direction is the force of friction. So that force of friction is in fact 1,125 newtons. So we can plug that in up here. And once you just plug that into a calculator and get our answer, we have a coefficient of static friction of 0.125. And there we go. So it's just figuring out, what forces are pointing in which directions, and then where can we plug in the values. Okay? All right. If you have any questions, leave them in the comments, or make sure you bring them up in class. I will talk to you guys later.